Here again, this is week number 3. We're going to cover Math Kernel Library. First of all, I'll just go into a little bit of everything else that's been happening. We're going to extend the time out for you to get your labs done and all the rest. We're a bit behind here, and I must apologize for that. We haven't put a lot of effort in because we've just gone through signing a term sheet and that sort of fun stuff. So we've just been running off getting external investment. As you might guess, running big computers with lots of electricity costs lots of money. So we now have people from overseas who are giving me money to keep those things running. So I apologize for the lack of focus in the last week, but we've just done a nice little deal that keeps us running for the next 5 years. And when you run 4 megawatts of electricity, that's a good thing, having a bit of funding for that. So we're going to talk a little bit about the Intel Math Kernel Library today. First of all, I'll just explain a little bit of extra what we're going to do. We're going to extend out, and I'll sometime later today, James will send you some details about what we're going to do for your labs. We're going to extend out the time. The actual lectures will be the same. We're going to do them over the same time period, but we're going to give you a bit of extra time to submit and get everything else done, and for me to get you access to other nodes, etc. I'll send today the IP address ranges for all the other compute nodes and things, so you can see what's there. They're on the 10.100 network and the 43. something network. I can't remember off the top of my head. Too many sort of scripted things these days. So that will be sent to you later today, which IPs they are, and by the end of the week you'll get the large memory node access. That has been delayed, so you'll get extra time, as I said. The reason being we've been off doing other businessy things, like actually raising money to keep the damn things going, which has been very successful. So we're quite happy and all the rest over here. That's where it is. So full details of extra time will be posted shortly after this. That won't change the fact that we're still going to be marking the end and giving out extra toys and how to use them and that sort of stuff. Plus I'll be loading up answers. I know I'm late. I do apologize, being grabbed away for the last week unexpectedly, and that sort of put a little bit of a crimp in some of this, but all good, and we're going to still keep going and give you some extra time to play. So we're going to talk about the MKL Math Kernel Library. Now, the Math Kernel Library is a combination of Fortran and other routines. These provide some of the mathematical, well, functions in the compiler that allow you to, well, do things like fast Fourier transforms for anyone who's done any of that sort of stuff before. Vector statistical functions, LAPACK, so calculating matrices. It includes all the LinPack results, which we've loaded ours now. That also took up some of my time in the last bit. We've gone through a system upgrade, part of the fun of doing all of this, where we have now got extra funding, etc. We're going to have some very happy SGI people, I think, because our system now has been funded for a few years, including power, at 3.9 petaflops. So we're going to find out the results of that before the end of this course, hopefully. The HPC Top 500 announcement will be in Germany. It's in about 2 weeks, just under 2 weeks from now, so we're going to find out what it is. Now, Linux and Windows, we have MKLs for those, so Math Kernel Libraries. They include all the standard LinPack stuff, So if you haven't looked at LinPack, I'll have to send some of that through. What this does is LinPack tests the speed using the solution of a number of matrix problems. There are better ways of doing it now, such as Strasson's method, but if you're doing a top 500 test, you're not allowed to use Strasson's method because they want you to actually have everything the same, which is understandable. At the end of the day, if everyone's running different versions, then it becomes problematic. So you can have my $1, okay? That's nice. I think we need a little bit more than that. All right, so anyway, as we're going here, the real reason of what we want to do in these systems is calculate a whole lot of math. All of our calculations on computer systems are really mathematical. Even when we're doing graphics or anything like this, it's all math. But in our case, we're looking at large data sets and multi-dimensional matrices, and the MKL libraries from Intel are optimized for use on either the Intel processors or the Xeon Phi. So, different things. For those who haven't looked at it before, I'll give some links so you can look at BLAS. BLAS are the basic linear algebra subprogram libraries. So things like vector operations, matrix and matrix operations. So multi-dimensional matrices. I hope everyone remembers all that fun that we had in high school solving matrices. Not just those little 3x3 ones we did in high school, but we're talking ones with thousands of different levels of routines. So sparse vector operations, etc. So if we're thinking about linear operations, then line diagrams, three-dimensional wireframes in CG, computer-generated images, all of these get solved. So one area that this is common that you'd probably see these days would be if you go to one of the common action movie type environments, something like the Jurassic World area, then you get to look at this fake creature that seems to look fairly real, not like the claymation things that we used to have in the past. And the first part of drawing all those would be doing an analysis of the wireframe and then putting flesh around that, doing shadows, etc. So, least square problems, eigenvalues, singularity, Sylvester equations, etc. All of those are available on Wikipedia for those who don't know, but all these things can be solved rather quickly. It includes vector mathematical library functions, so either C or Fortran, vector statistical libraries, so pseudo-random numbers, statistical distributions, not just standard Gaussian, but all the different types of time series analysis, G-arch, or something such as binomials, power series, etc. General fast Fourier transform functions, so looking at discrete Fourier transforms in engineering analysis, looking at flow dynamics chaos, and by chaos we're talking about chaotic results, things like not actually random, but fractals, for instance, analysis of fractal type results, or fluid dynamics, looking at partial differential equations, trigonomic transforms, Poisson solvers, etc. All of these are part of the Intel MKL library. And this allows us to, well, really pull this together quickly. So we have decent precision. It can go from an engineering point of view without losing too much data, and well, we can solve all types of information quickly. Recently, over in Texas, I believe, there was an interesting little exercise where the Defense Department allowed a number of scientists to jump on one of the big computers over there, and what they did was actually solve around 1 billion unsolved mathematical algorithms. Not that they're ones that couldn't be solved, people could have with enough time, but these are problems that would have taken a long time to manually solve. So how to do audio pattern matching like Shazam? Well, at the end of the day, then you're looking at a statistical match. So generally when you're going to load audio, you're going to load something like a waveform, and you can either do different types of Fourier analysis, or you can look at time series over how the wave changes over time, different types of statistical subroutines. Really depends on what you're actually trying to match with your audio pattern. So if you're trying to get rid of any errors, find background noise, extract maybe voices in the background, analyze voices in the background, all sorts of things you can do with all of this. So separate waves from waves is one thing that people have do with these sort of systems for audio pattern matching. From a music point of view, people extract individual instruments and re-add them. So all of that can be calculated and approximated to a level that even the human ear can't actually tell if you want to put enough effort into it. So parallel blast routines, I recommend having a bit of a read on those, so you can do a search on level 1, 2 and 3 blast routines fairly easily. LAPACK, ScalaPack, etc. routines for both Windows and Linux. In this case, of course, it's going to be Linux. I've also got a nice big workstation here running Windows. It enables me to do a little bit of calculation the same. The thing you'll find with Windows, though, although it does actually allow you to do MPI, it's sort of a micro Linux architecture, so you're working on a Windows machine and then interacting with Linux in a way anyway. It's a micro Linux interaction, so it's still there. And then we have cluster functions to interact with all that over different systems. So documentation, that will be loaded up and linked for you shortly. I will give the user guide and whatever else for, I believe it's on the documentation I've sent already, if it hasn't been put up there by the good guys at IT Masters. I'll make sure it is. I'll check through that this afternoon, but there are lots and lots of pages. So the MKL manual is 3,460 pages at last check. It's quite large. So lots and lots of reading. I don't think many people know it inside out. A few might, but the user guide is long enough. It's 127 pages, so not short. So we have a number of scripts. We can run these things such to set them up. So our compiler libraries allow us to set environment. There's a C shell and just a normal bash shell type version of doing it. If we were running modules, which I'm going to have to go over before this is done, what I'll do is a separate loaded lecture before the end where I show how modules work. You can run that, which I haven't loaded for you guys at the moment. And there are different versions, of course, like everything else. Running old versions don't work quite as well. Got a question here for the lab work. Do we have to submit our results somewhere? If so, where is that? Next week, I will go over what you need to start planning. So the first 3 labs are really practice for you to get familiar with things and start working on it. It's the final lab number 4 that you'll have to submit. That will go to or basically the guys at IT Masters, and then that will come back to us, and we're going to have to start pulling that apart and going over how we're going to market. So I'll explain how we're going to market and what we expect next week, and what sort of format we want for you to get the best results. You don't need to submit, but if you do submit, that's where we're going to pick the best 10 people and give you a little bonus. So one of the things I will also do, we're going to do a video that Ray in the background there that you can't see, but we've got a video camera and he's sitting there in the background. He's going to be filming me going over some Xeon Phi cards later in the week, and we're going to talk about those and pull some out of the boxes and explain how they integrate, what happens, how you pop them in the system and run them. So will the final lab involve Fortran? It doesn't need to, no. You can use Fortran, you don't need to. The majority of this will involve C++, and we're going to mark you on C++. If you want to do any extra just to show off, well, I'm not going to stop you. Okay, so there are many different libraries. Of course, we can look at the standard larger ones in 64-bit world. We have 4 different layers: interface layer, threading layer, the computational layer, and the real-time library layer. And it's not as complicated as you think, although it seems that way. Now, you can choose your libraries and options based on a little bit of a software thing that they actually provide. So if you go to softwareintel.com, there is a MKL link line advisor. So you don't need to actually make life as difficult as it can be. You can find solutions yourself. Anywhere to buy Phi cards? Yes, you can buy Phi cards. Phi cards are available all over the place, like buying a CPU. I don't think they're selling them into China for some reason at the moment, and definitely can't buy them in Iran, but for the main part, you can go on to Amazon and you can buy a Phi card there, either the 3, 5 or 7 series, and as long as you've got a system that has a fast enough bus and enough memory and enough well, everything else, then you're fine. The difficulty in many systems is the power. These things chew up a little bit of power, so you need to have a large enough what do you call it, PSU in there, and then you're okay. So include paths. MKL setup scripts load everything for you. They're in the /include area. Fortran 95 is a little bit different. Lots of reading on these if you want to get familiar with them. So there are 2 different ways of linking this, of course. We can either link them as a static or dynamic. Now, there are many benefits in isolating and distributing things by doing it in a static environment, except for one little problem, that you have to update everything and redo it fully. So dynamic link libraries have many benefits, of course, as well. They mean that you need to make sure that the machine you move things on to have the correct libraries, whereas if you have the big, ugly static chunk that you link everything together with and build it into one pile, you can move it around to many systems, but that's always a choice. So some people like to actually build static library for certain security reasons, or if they're moving them between systems. You don't need to necessarily have all the libraries there, but one of the difficulties when you have a dynamic linked system is you can upgrade a single library or whatever else without having to worry about everything being upgraded at once. Just updates are a little bit simpler. So there are many examples in the MKL root area. Poisson is one of the common ones I work with. I'm assuming people know what Poisson is used for. Common area would be queuing theory, and I'm hoping everyone knows what queuing theory is. I generally get myself into trouble when I start assuming that people know these things. In queuing theory, you're looking at something like modeling people coming in and out of a queue, would be the simple way of putting it. So a call center type modeling, the probability of how many calls coming in, how many customers coming in, how many people waiting in line would all be calculated using Poisson. Other areas I have actually used it would be modeling software failures, modeling vulnerabilities, and modeling how robust a system might be. So, and for those who know anything about Bitcoin and the blockchain, then how quickly transactions get taken up, and modeling that is a Poisson probability distribution. So your different areas: BLAS, BLAS 95, CB, CBLAS, CD, FTC, etc. Many different examples that you can use as templates there. So running an example, which basically looking at BLAS from the example BLAS library there, you can look at BLAS first, data, makefile source, run without arguments, or tune it a little bit as we go through the different examples in the labs. You'll get to play with some of this more. The example that they have as a MKL example one is just a simple test program. There's nothing particularly complex here. XYA, just calling, writing, very simple to test, so it gives you an intro. Your makefile will include just general paths to the libraries there. Once again, we create test one, link it, and away we go. There's a Fortran example for those who prefer Fortran as well. You don't need to do Fortran for this, but Fortran is still very common in this sort of world for some reason. I can't seem to get rid of it myself. Damn thing pops up. It's used quite commonly in the engineering world. There's a lot of mathematical libraries and all the rest. We've actually done our best to write a whole lot of C++ libraries instead. I'm still much more of a fan of C++. I don't like Fortran. Probably the fact that I went through engineering at Queensland Uni way back in the, well, end of the 80s, beginning of the 90s, and had a whole lot of people who could hardly speak English trying to teach me Fortran, probably put me off it for life. Okay, shared memory programming. So then after this we're going to cover OpenMP. Now, for those who haven't had a bit of a look, I recommend you go to the OpenMP pages and have a bit of a read. OpenMP allows you to, well, run code in parallel across different cards, different systems, different cores. Now, remember, as I said, these are going to be multi-core systems that we're running on. Yes, I know you haven't got access yet. Again, apologize for all of that. We are going to be opening that up this week and giving you extra time to play. Do the MKL libraries use OpenMP internally? Not from my understanding, the MPI libraries used by Intel are actually customized and created by Intel, so they're optimized. So there may be some code overlaps. That bit I can't actually say. Generally, with many Linux systems and other such things, people do overwrite, but maybe not. So don't actually know. I haven't really looked at the MKI libraries to compare them to OpenMP. They are very similar in some ways, but I believe the optimizations are sufficiently different from Intel, but that would be something someone else would need to answer for me, maybe an Intel person. Okay, so write parallel code using OpenMP. OpenMP is free. You don't need to pay for it, of course. The open libraries there are, as it says, open. So it's been around for some time. 1997, there were no standards for shared memory parallelization. So everyone came up with their own. I don't know if people have remember the past. Some different systems that were available would include Sun had its own. So anyone remember Sun Microsystems before Oracle took it and pulled it apart and kept the bits they wanted, like Java, etc. Then we had Silicon Graphics, not like we have now. We had in the past Silicon Graphics, rather than being a big open, I guess, Intel Linux machine, they used to be in the past their own special PowerPC or other alternative RISC processor running IRIX. So back then, before they had their first problems and got bailed out, they were really running something different. So MIPS, yeah, as Reagan has pointed out. That has changed significantly. We've really standardized. There's not many chips anymore. The IBM guys are still running their power chips, but AMD and Intel seem to be the main competitors. NVIDIA are still out there for the CUDA world, and we've moved a long way. So parallel, we're going to be running code vectorized and all different things at once. All right, so anyway, Fortran was the first version of OpenMP to come out. That actually got released by SGI. So SGI then implemented a OpenMP implementation for C++ and C, and that's extended from there. Intel and others jumped on board. So one of the best things that happened was it got put out there to the world. So the SGI guys chucked out the standard and allowed people to use it for free, and since then things have been opening up and lots of people use it. So the parallel programming execution model for OpenMP is a fork and join execution model. Starts with a single master thread, so it's like the old tree model. So like a Christmas tree, it branches out into different areas. Parallel threads are executed by a team of threads, one after the other, and then it comes back and rejoins. So allows you to have loop level data parallelization as well as function parallelization. There's a good write-up on Wikipedia. As much as I hate Wiki at times and bitch about it, it's starting to get better on general everything that it's doing. A lot of information there. That bit I'll definitely say, and the write-up on this is quite good. So OpenMP is very scalable. It is both fine and coarse grained for parallelization. And just one of these days where I'm saying these things wacky. The emphasis is on performance, which is very good. The idea is more to have how fast you get things. So the benefits of how quickly we can run is what it's about. It's good for shared memory. One of the key strengths with the SGI boxes, the ICE, the IceX, etc., like some of the ones we run, are they allow you to whack memory together and run that way. And library calls, environment variables run together. So directives, you've got the Fortran ones, or you've got the C ones, Pragma, OMP, Directive, where you add a structured block after that. When we're using it, OpenMP, so we call macros. We're not going to be able to do hash define or undefine in that. We can call that using a underscore OpenMP macro. And what that does, if you have a look at the simplified version of things here, you start, you branch out, and then you rejoin. So if you're doing multiple branches or loops or anything like that, you're then branching and branching and branching. C++ you need to be careful with. C++ is one of these languages where if you do it wrong, you can shoot yourself in the foot. Unfortunately, there's always good and bad to that. I'm always a fan of C++, but that's where we go from. Now, OpenMP executes as a single master thread. So when we're looking at this, the OpenMP parallel directive is started. When it's encountered, it branches to how many cores we can actually chuck it to, what we're allowed. So if we're thinking about a single PHY card on a machine where we have, say, a 7120p, we have 61 cores, 60 usable, 4 threads per core, then what we're looking at is 240 potential threads. So we could, if we had our thing tuned right, OMP would split that off into up to 240 individual process threads and run that as redundant code in parallel. So parallel but redundant. Master process will then continue and allow us to finish that till we finish. Once we get our answer, everything is rejoined and pulled back together. So effectively what we're doing is a thread team. So that allows us to execute parallel region, pull it all together and rejoin into our single master. Now, our problem, as I said, is if we have a C++ throw inside a parallel region, it needs to be caught in the same thread. So where we're looking at this, if we have a throw in one of these particular threads there, it needs to be caught in the same thread and continue execution inside the dynamic content of the same structured block. So it's no good putting a throw out. It can't be caught by one of the other threads. So that's just a little gotcha when we're talking about C++. So clauses, we have private, shared, default, first private, reduction, those sort of things. What we need to do when we're thinking about how we analyze and execute parallel regions of code is thinking about how we scope the data items by default. So what we do to create each thread, we need to allocate storage for that thread, its own private list potentially, declare any variables in first private list. Variable will be private, but initialize to the value of the same variable in the master thread. Remember, we have to put everything back in the master thread at the end. We cannot, well, we shouldn't overload anything in C++, but anyway. So variables listed in a reduction clause, special private variable is created and initialize for each thread. So once we get to the end of a code region that we're using, we then reduce the partial answers from each thread to one final answer, and then redact that together and come back and rejoin what we're doing. If we have an if clause, so we're branching, the region will only be executed in parallel if we have a scalar logical expression that is set to be true. Now, we may actually have a region conditionally executed in parallel. The reason for that would be where we have work vary from run to run, or even within a run, and copying clause then causes common blocks that have been declared thread private and variables of whole common blocks in the list to be initialized within the master thread. Thread private is a special declaration that we can put in there to follow a declaration of variable that we set to private. We do this when we have a parallel region, but where a value needs to be retained between parallel region invocations. So private variables are generally set automatically, created each time a parallel region is entered and run and destroyed. And once we do this, what we end up with is something like, here we have the Fortran do, or probably should have that. Yeah. Right. All right, I have to change that afterwards. Got a little bit of an overwrite on the image there, but we'll have to move that. So do is a natural way of actually running the for type loops in Fortran. OpenMP 2 allows us to have a distribute clause in our compiler. So you can't really see that terribly well, but we're looking at the Fortran sort of block here, do 1 to n, do, so we can split those off. And one example of what we could do for our for loop here, we could branch off. So instead of running each of these one by one, as you'd normally do on a computer, you'd run through, you'd go I equals 0, I equals 1, I equals 2, up to I equals n. We could actually have the compiled version split that out across many systems. So we could simultaneously, and here we've got 0, 1, 2, 3, etc., thread branches all running on our for loop simultaneously. So we could actually have those all happen at the same time. So just a little bit of the wonders of sort of compute systems. So OpenMP, the for command allows us to do these things simultaneously, in effect. We can schedule everything together, work through what we get, and order it in such a way that we really run all of those different loops simultaneously. So it just allows us to get back results far quicker. So if you think about what you might do when you're running a normal program on your system, instead of having a for loop sequentially go through 0, 1, 2, 3, 4, whatever else, if you have, say 5,000 cores that you've had allocated, you could simultaneously run 0 to 5,000, calculating individually on each thread and return a result at the end, and as you might guess, that should be a little bit quicker. So scheduling types, here we see static and chunk size not being specified, but one chunk going off to each thread. So in this case we're doing a for loop from 0 to 1,000, and we've split everything up. So instead of doing well, sequentially 1,000 operations, we have 250 sequential operations. So things have sped up a little bit, we hope. We've chunked off each bit and we have created a thread of I equals 0 or 1 to 250, I equals 250 to 500, etc. And we can run it all at once. So you can see just the idea of what we're trying to do when we're parallelizing. Now, different ways of scheduling. If we use static with chunk size, we could schedule our blocks based on different expected times when we, well, trying to make everything match up. So here, what we're looking at is, well, trying to match up these little chunks so that we optimize the threads and return things as quick as possible. Sometimes you can't, sometimes you can. Can't always say. So if you look at the results here, synchronization barrier, when it returns control and we go back to the master thread, if you look at what's happened in optimizing our code, we've moved things back from where it was there at a longer time to, well, move the optimization around. So instead of having large things all in one thread, we go and we move that large one from there to there. And if anyone's done any project management work or anything like this, what we're really seeking to do here is minimize the amount of time that we're running everything on our system. So we're trying to minimize the processing time. So when we're looking at this, we may have these idle loops here, but there's a bit of a gap there. So we've started this thread, we started a core, we have a large wait time that's doing nothing, so we have an idle core being wasted. By optimizing this, we can return the processing, free up the either CUDA or PHY cores or whatever else we got, even our CPUs, allowing us to go back and start processing something else on those systems. And when we're talking about shared systems, etc., then we really need to think about how we do that, because shorter execution time means we free the system up and allow it to be used faster. So that's what we're trying to do. So once again, scheduling types, we start with large chunks, we look at different sizes, and we optimize that so it runs as well as it can. So, whoops, what way did I do that? Okay, auto delegates decision regarding scheduling to the compiler. That's probably the simplest way of doing it. We don't need to think too much at all. Programmer gives the compiler the freedom to choose any way of mapping iterations to threads in the thread team. So that's the simplest way. We can start manually setting all this ourselves. That's where we start setting the runtime variables, but we have both options. So work sharing, we have a structured block A, B, C, D here in our diagram. Another method there of using multiple processes is to have them execute different regions of code. This is known as functional parallelization. Each section of code is executed by a thread. Threads will synchronize at the end of the section directive unless there's a no wait clause. So sections directive has clauses similar to the do directive that we have, like a for directive or whatever else in C++. So when we're looking at work sharing as a single, it's an implicit barrier at the end of the single section. So the first thread arrives at the single directive, executes the code block. All other threads skip this block and wait for the rest of the team to reach the end of a single directive. Waiting can be overridden if we put a no wait clause in, and that takes us to the end of a single directive. So I'm pointing with my hands here. which is great on the film video, but you can't see that. So back to the mouse here. What we have is something jumps around. You can see the arrow there, waiting, etc. Alternatively, we can have a master directive. We can force the block of code to be executed only by the master of the team. So we can choose which particular way we go. The rest of the team skips the block and continues processing. So this block of code here gets executed on a thread and all the others skip past it. Okay, other things, we have Workshare constructs, which is Fortran. I won't go into that too much there unless people particularly, if you want to play with that, if you want to go into Fortran, that's fine, but I'll skip past that for the moment. OpenMP tasks have been introduced really to allow dynamic work sharing. Now, it really allows irregular problems to be parallelized. There are lots of things out there that are not structured. This is real world, and many problems will find we don't have a nice simple structure to what we're going to do, and OpenMP allows us to parallelize many of those. Okay, taskwait allows, it's a construct that specifies a wait on the completion of a child task. There we see the C pragma sort of way that it works, hash pragma there. Task example, hash pragma OMP parallel, pragma OMP simple, while work to do, so while whatever we have to do work, call our function, etc. Work sharing shorthand, so either in Fortran or seed at the bottom there. We can see this, it's quite common to have the following in OpenMP programs. You can notice this is in Fortran, of course. A few other ways of doing it, do loop, do loop, do loop, etc. There can be a lot of overhead in starting and stopping parallel regions. So once something's started, it's best to push as much work into a section of parallel code as possible. Orphaning. So here we're doing our routine foo. So subroutine called foo there. Work sharing constructs can be called outside a parallel region. So if foo is called from outside a parallel region, the do loop in the Fortran example is executed by a team of one, the master. Foo cannot be legally called from within a work sharing do loop. So when we're calling these things, we have to set how it's called and what we can do. Data scoping clauses, just a few ways of doing things. I won't go too much into this much more. Synchronization is important. All threads in a team will wait for each other at the barrier directive. Threads wait at the beginning of a critical region until no further team members in the region are available in processing. So as we're doing this, we'll find that the critical directive has an optional name and all unnamed critical sections map to the same region. So when we're looking at C++, the hash pragma OMP barrier must be in a structured block. It's not a statement, and something like if x bang equals 0, pragma OMP barrier would be illegal. So different aspects here. We have atomic, so count +1. We want to make sure we have memory consistency maintained, thread count maintained, and synchronized between our threads. So in C++, binary operator for the atomic update must be one of the following, plus multiply of star, minus, forward slash or divide. In other words, the ampersand or and function, the caret function, which is a power function, something to the power of, the logical OR function, bit shift functions, the double right angle bracket type things, and in C++, binary operators can't be overloaded. So just something to remember. There are a number of implicit flushes with no list at a barrier, at entry and exit of any critical regions, exit of work sharing constructs, but generally speaking, the synchronization mechanisms, the more heavyweight mechanisms like barriers at the end are going to be most expensive. Now, those barriers do have the advantage that they are less likely to yield correctness problems. So generally, when we compile, we're not going to have any problems with not releasing memory, etc., etc. But if we do use synchronization variables or locks, we can find that our code can be much faster. It's just more difficult to ensure that problems like deadlocks never occur. And we can actually end up with deadlocks. So synchronization, do for ordered, something to bit of a look at there, and some of the different options. So Intel compiler for OpenMP version 3, we have the -OpenMP, gives us the OpenMP directives, OpenMP report, etc. So these that you see there, those 5 options, are not the complete list of OpenMP compiler options for the Intel compiler. If you do -OpenMP-lib, -OpenMP-link, or -OpenMP-thread private, you'll find more. You can also adversely affect performance if you use OpenMP profile incorrectly. The additional profiling and error checking that is invoked with that can well, basically stuff up how your threading works, and you need to be careful when you're using the OpenMP directives manually. So mixed options, you can actually call OpenMP in parallel simultaneously from the command line. The parallel option is only applied in loop nests that do not have OpenMP directives. When you do, Intel compilers support hybrid programming, which is using OpenMP and MPI simultaneously. So you don't have to lock yourself into the OpenMP. You can use the MP Intel libraries at the same time. When you do this, parallelization is available within a node, and MPI is used to communicate between the nodes. If you have a look at the Intel cluster MP in distributed memory systems, there's a bit of a write-up in there, and there's many, many pages of documentation. Environment variables that you should know. We have the OMP threads, scheduled, dynamic, and nested. You can see what they do in each of these. So OpenMP, parallel, etc. are all there. Stack size, etc. I'll leave this for you to have a bit of a read through. We can set stack size in bytes, kilobytes, megabytes, gigabytes, and terabytes to specify units, with the default being 4 meg. KMP, so how many threads we're going to execute in a program, block time, milliseconds, KMP libraries, version, stack size, whatever else we're going to use. The OMP stack size does not affect the native operating system threads created by the user program, nor the thread executing the sequential part of an OpenMP program or parallel programs created using -parallel. KMP stack size overrides the OMP stack size variable, just to add a little extra something for you to read up later. OMP stack size does not affect native operating system threads created by the user program, nor the thread executing sequential part of an OpenMP program, parallel programs created using -parallel. So runtime library routines, execution, environment routines, lock routines, timing routines, and extension routines. Lots of them to have a bit of a look at. I won't go into too much detail on each of these at the moment. Many calls for nested loops, etc. Lots to go into. I'll leave you to read up on these, double OMP get, etc. The extension routines, the stack size routines, memory allocation routines. Gotta love C++. Block time, and etc. So other bits and pieces, useful information for OpenMP. Performance is really going to be dependent on thread placement and the number of threads per core. So how many threads you have per core matters. The environment variable KMP infinity really helps set how we run. Performance of many applications on the CPUs is limited by memory bandwidth. So how much memory there is between the bus between your CPU and your memory, how much L2 cache you have available is very important. If you're doing too many handoff between a CPU and a FI card, or CPU and CUDA cards, or whatever else, that's going to be important, because the memory bandwidth inside a NVIDIA or inside an MPI, the PHY, is going to be far greater than the bus memory between well, the CPU and the offload card. So you've got to make sure that you have that right. Even if you're basing it on your own CPU, then L2 cache is critical here. So we find it's not too unusual to see applications running with one thread per L2 cache outperforming the same application using 2 threads per cache. So when you're setting all of this up, it becomes very critical to start thinking about how many threads you're going to have per fast memory access lane. So if we're running a 2-thread application, there are 3 possibilities: each thread on a dedicated socket, each thread on a dedicated cache, both threads using the same cache. And depending on what happens there, we find that the performance will change radically. Okay. Next week we will continue with compiling for shared memory parallelization. And I'll be sending some extra links, materials, and whatever else to James. Now, why are there no successful data parallel languages? Everything is environment, variables, compiler options, pragmas, and libraries, not actual language like C. See, I think that's, I'm not sure if that's star or hash, C star. Okay, coming up too small. Why are there no successful data parallel languages? I think it's rather complex. So everything follows Moore's law when we're talking about hardware, but the reality is when you're talking about parallelization and vectorization, then for what? Which system? And it changes very quickly. Well, maybe if we're looking at CPUs with 18 cores, 2 threads per core per CPU, versus say a K80 with 4,992 cores, etc., then which one are you designing it for? It becomes so complex in software. So software is still way, way behind the hardware, and we're not really growing at the same pace. So hardware is increasing at the speed of Moore's law. Software isn't. And I'm sure if someone solves that, they'll be very, very famous. But right at the moment, why are there no successful data parallel languages? Because it's so complex. There's so many different options, so many different ways of mucking up software, so many ways of deadlocking systems, so many ways of optimizing things. And it really comes down to complexity at the moment. There's not a simple answer. Like we can have compilers do some of it for us, but there's no simple answer. Okay. I guess that's really the end of all this for now. I will be going back and getting some extra stuff up shortly, and going over and making sure that you've got some extra to go on with. And the good people at IT Masters will give you some more information shortly on what we're going to do lab-wise and how much extra time you've got to break things on it. And that's really about it for now. Any last-minute questions? No? Anyone typing away madly? Nope. Great. Is the slowness of the machine going to be addressed? Yes, we're looking at that at the moment. I'm not sure why things have slowed down for you, but I'll make sure if Wen or someone else has been doing some testing or whatever else, I'll look into that. 60 seconds to log in. I think that might be something to do with SSH and DNS. We have an internal DNS domain, so